Hello everybody, this is Mr. Fasoni. This will be the first of several videos regarding our Algebra 2 topics. Like I said in class, these are going to be asynchronous, so you'll be watching these in the afternoons or evenings in a time period where you're not technically in class, and using this to get started on classwork / homework that I assign. And then the following class period after this is assigned, you'll be bringing your questions on the content, and we'll be talking more about the content in class together. So let's get started. This is chapter 1, which is about linear functions and functions in general. And chapter 1.1 specifically is about parent functions and transformations. So our goals for this chapter are to identify families of functions, describe transformations of parent functions, and describe combinations of transformations. There's some previous vocabulary from Algebra 1 and prior that you may need to review, but I will briefly talk about them as well in here. So our first one is a function. A function is one of the most important concepts of all of Algebra 1 and Algebra 2, and you'll be using the concept of a function as you go into trigonometry and calculus and beyond as well. And a function is basically just a relation that pairs each input. So by input in this case, I mean an x value with exactly one output. And our outputs in this case are y values. So for instance, you could draw a circle, or you could have a list of values. These are x values, 1, 2, 3, and 4. And let's say I've got some y values over here. Let's call them A, B, and C. They don't have to be numbers. They could be named values. This is just representative. So when I plug in a 1, maybe my function kicks out the value A. Maybe I plug in a 2 and it gives me the value C. Plug in a 3, maybe I get the value B. And maybe I plug a 4 in and I also get the value C. This would be a function because each input, 1, 2, 3, and 4, is connected to exactly one output, A, B, C. A couple of the inputs, 2 and 4, both go to the same output, C. That's perfectly fine. That's still valid for a function. There's no rule saying that an output has to be connected to only one input. Functions only really care about the inputs. Here's an example of a function that is not working correctly. I've got the value 1, and if I plug it in for my input, for my x value or my input, and I get 3 different y values, A, B, or C, when I plug in 1, then that's not a real function. A function needs to behave the same way over and over again. When I put a 1 in, it should always give me a single value back. If I get different values back, then that is not working correctly. So once again, this is a function. This is not a function. All right, so that's our first idea. Each input is paired with exactly one output. Domain. A domain of a function is just a set of all possible input values of the function. A lot of times in math, especially with what we're working with, the domain will be all possible values of x. You can be at negative 34 trillion, you can put 1/2 in, you can put 112 in, you can put 2/3 in. Any input value would be part of the domain. Sometimes the domain is limited. Sometimes we only want maybe positive numbers or within an interval. But a lot of the time when we're working with functions in Algebra 2, the domain is going to encompass all numbers. And then the range is going to be the set of all possible output values of a function. The range can sometimes be all y values. Sometimes it can be all positive y values. It can be all negative y values, and various other ranges as well. And then finally, content from before, vocabulary from before is a slope. The slope is something that we see a lot with linear functions. It's going to be the rate of change in y divided by the rate of change in x. Some people might also call that the rise over the run. Or you could say, if you wanted to do an equation, if you had 2 points, let's say I had the points x1, y1, as well as x2, y2. I could do an equation. I could say, okay, my difference in rise, take y2 minus y1 and divide it by x2 minus x1. That would give me my slope, which we denote with the letter m. Remember the slope, remember the slope is used in a couple different equations. You've got slope-intercept form, which is going to be y equals mx plus b, where b is your slope, your y-intercept, and m is your slope. And then you've also got point slope form, where you've got y minus y1 is equal to my slope m times x minus x1. In both of these situations, we've got the slope. In this one, we've got the intercept, which is b. In the other one, we've got the point, which is signified by the x1 and y1. We'll get more into those at a later time, but I just wanted to do a quick review on those terms. So, new concept, parent functions. So parent functions are the basic functions that we can take and then manipulate to create new functions that have similar shapes and behaviors when we graph them or we look at their domains and ranges. So our first function, which is the most simple type of function, is called a constant function. A constant function is basically saying, when I plug x into a function f, remember the name of the function is always denoted on the outside, and typically we use f when we're giving examples for functions, but we can use any letter we want. So if I've got a function f with an input of x, f of x, if it's a constant function, the output on the other side of the equation is just going to be a constant value, just a number value. So what that's saying is, for this constant function, no matter what x value I put in, my y value, my output value, is going to be 1. So if I plug in, let's say a 2, I'm going to zoom in on this. Let's try this out. So here's my function, or here's my graph. If I plug in, x equals 2 into this function, remember the function was f of x equals 1. It doesn't matter what my input is, it's always going to output a value at 1. So if I were to graph it, when I input a 2, I get a 1 out. When I input a 5, I get a 1 out. When I input a negative 6 for my x value, I still get a 1 out. And any other value for x, fractions, decimals, 0, no matter what, I'm still getting a y value, an output value of 1 out. When we talk about functions, we're always talking about using some input, which we usually use x for. The reason we use x is because we think of it as a number line. We pick a point on the number line. For instance, I pick the value 2 on the number line. I plug it into my function. I do some math. It kicks out an output. In this case, there's no actual formula. It's just always kicking out the number 1. So I input that value 2, and I get a y value, an output value of 1. I can graph those, and that will give me the shape of my function. We call these shapes, these general shapes, the function family. All functions of the family, constant functions, all have the same shape, and that shape is a horizontal line. If my constant instead of 1 was, I don't know, 23, it would work the same exact way. It'd just be another line that is higher up vertically. Can I add arrows to that? Let's see. Not very good, but it works. So that would be my constant function, f of x equals 23. So that's the simplest function. Next up, we're going to go to linear functions. Linear functions, their parent function is just going to be f of x equals x. It's a linear function, so if you think about something like point slope form, or better yet, slope intercept form, that f of x equals x, well, all that's saying, if you think about it as y equals mx plus b, in the case of the parent function, my m value would be a 1. 1 times x is x, and my b value would be a 0. So my slope is 1, and my y-intercept is 0. That parent function looks like a diagonal line sloping upward as we move from left to right. That reminds me, when we're working with graphs, we always view graphs and read graphs just like we would read a book. We read from left to right in a book. We're going to read from left to right in a graph. So as my x value increases as I go from negative to positive, just like along the number line, my y values are going from negative to positive in this case as well, which means I've got a positive slope, which makes sense because, like we talked about before, my slope in this case is 1, which is positive. So for every 1 I move up, I rise 1. For every time I run 1. And again, if I were to plug in a value, if this is just the function f of x equals x, that means for every x that I input for my input into the function, the value I'm going to get out of the function is the exact same value x. So if I input a 3, my output value is going to be y equals 3. And when I graph that, input a 3, output a 3. If I input an 8, I'm going to get out an 8. If I input a negative 15, I'm going to output a negative 15. And if I put all these points together, all the decimals, all the fractions, that creates that shape of the function when we graph it out of a diagonal line. And the parent function moves upwards, but as we'll see later on, those can also be downward slopes, steeper slopes, more flat slopes, etc. Okay, next up, we've got our absolute value function. You should remember this from Algebra 1 as well. This is just saying the f of x is equal to the absolute value of x. Now remember, absolute value is basically asking how far is this value x away from 0 on the number line. An absolute value, since it's talking about distance, it wants a positive value when we talk about it. So again, I can plug in any value I want. Any of the positive values are automatically going to return a positive value. If I'm 3 away from 0 on the number line, at positive 3, that means I'm 3 away from 0. So it would be 3, 3. When I'm over here at -7, even though I'm negative, the distance, if I were to measure this distance on the number line from 7 to 0, remember 0 is at the origin, that distance is going to be 7. So my input is a -7, but my output is the absolute value of -7, or +7. This results in all values on the absolute value graph for the parent function being either positive, or in the case of 0, the only case that's not positive, 0, 0 is neither positive or negative. And that results in this shape that looks like a V. We're going to be using this shape a lot in this section because the shape allows us to see where our graph moves around. It's harder to see transformations on linear functions, but absolute values are very nice for that. Finally, we've got quadratics. Quadratics have a shape like a parabola, a curve, and that's because we're using x to the second power. So any x input that we use is squared before we graph the y value. So for instance, if my x value is at 1, oops, my x value is 1, my input is 1, that means my output is going to be 1 squared, so 1, 1. But if I'm over here at 5, 5 squared is going to give me 25, which is going to result in this rapidly increasing y value, which results in the curve getting steeper and steeper as you go away from 0 on the y-axis. Since we're squaring, we also know that a negative times a negative, negative times itself, is going to be a positive. So if I plug in a -3, for instance, I will get a +9. We'll deal more with quadratics in chapter 2, 3, and 4, I believe, or at least 2 and 3. So we're going to be dealing with those a lot. We also have the domains and the ranges. For constant functions, the domain can be any x value. I could plug in -300 billion, I could plug in +1 million, I could plug in 0, it doesn't really matter. Any input will work, and my range is always going to be a constant value because the y value is always the same when we have a constant function, so that y value is going to be 1 for the range. Linear functions, since they move uphill and downhill, any x value can be input, and the range can be any y value. As I go way over here to the upper right, my x and y values are going to get bigger and bigger. If I go to the lower left, they're also going to get smaller, or more and more negative. I shouldn't say small. They're going to be very large negative numbers. Absolute value is a little bit different. For this parent function, I can put in any x value, but remember, it's always going to return either a 0 or a positive value for my y values. So my range is always going to be greater than or equal to 0. Quadratics work the same way as the absolute value. Since I'm squaring my input, I can put in any value, but if I square a negative, it's going to turn positive. If I square a positive, it'll stay positive. And if I square a 0, it's going to remain 0. So again, my range on a quadratic function is going to be all y values greater than or equal to 0. All right. So our goal number one, one of our things we're trying to learn in this section is how to identify function families. So we want to identify the function family to which the function belongs, and then compare the graph of the function family to the graph of the parent function. I'm going to zoom in on this left one first. We can just look at the shape. We can look at the equation as well and see what parent is in there. But if we have that distinctive V shape that comes to a point, then we know it's going to be an absolute value function. So it's absolute value. We know it's going to be an absolute value. That's what family it belongs to. And then we want to compare it to the parent function. Well, let's graph the parent function. We know the parent function, f of x, or let's call it just the parent function is the absolute value of x. If I'm at 0 for x, what did I just do here? If I'm at 0 for x, my y value is also going to be 0. If I'm at 1 for x, then my y value for x is going to be at 1. It's blocked by this little speech box. If I'm at -1 for x, my y value is still going to be +1 because the absolute value of -1 is +1. If I go to 2, my output will be a 2, -2, also a 2. And I can go back and forth graphing these as long as I want. And since we know the shape of this function, we can then connect as best we can to make our graph of our absolute value function. So this graph in red is our parent function. The graph in blue is the one we're comparing it to. Well, there's a couple differences. I noticed that the point of my parent function looks to have been moved up by a value of 1. It moved from 0, 0 to what looks to be 0, 1. And then also, if I look at my graph itself, it looks like it has gotten steeper. It looks like somebody took the graph and stretched it in a vertical manner, which made it change from kind of this large, I'm going to use a kind of a geometry representation really quick. It looks like we've got kind of this large angle here for the red function. But if I look at the blue function, it looks like the angle has gotten narrower. So if we want to describe what's happened here, I could say that the graph, well, how it compares, I should say, but the graph is moved up or moved vertically I'll put up in parentheses. It could be moved down vertically as well, and is narrower than the parent. Function. Remember, our parent function is the absolute value of x. I forgot a D there, moved vertically up. So that's a basic description of what's happening in this first one. Let's look at the second graph. It's also a little bit different. I've got h of x equals -3 times x minus 2. Well, if I look at the graph, just comparing it to our chart from earlier, it is going to be a linear function. We know it's going to be a linear function oops. We know the parent function of a linear is just going to be the function x, or you can say f of x equals x. And if I were to graph that parent function, it would look something like this. When I plug a 0 in, I get a 0. When I plug a 1 in, I get a 1, a 2, 3, and 4. But also if I plug a -1 in, I get a negative value, and oops, and so on and so forth. And then I can connect these. Just going to draw a line here. It's not the best. But if I connect these, I get a function that goes up and to the left. So if I want to describe them, there's a couple different things I could say. I could say that it differs from the parent function. My blue line has a negative slope. My blue function, also called h of x, has a negative slope. And it looks like it was shifted a bit too as far as the intercept goes. My red function has a y-intercept right here at 0. That's where it crosses the y-axis, but the blue one has a y-intercept up at 6. So it has a y-intercept of 6 instead of 0. We're just describing what we can in this situation. So that is our first goal in this class, is to be able to discuss what function family a function belongs, and then compare it, the function to the function, the parent function of that family, and describe that difference. So let's talk about, we've identified, let's talk about our next thing, which is probably our big topic for the section, transformations. Transformations are much more specific ways to talk about these changes that happen to our parent functions when we make a new function. So a transformation changes the size, shape, position, or orientation of a graph. And there are 3 different transformations. We call them translations, reflections, and stretch or shrinks. I should have pluralized those, stretches or shrinks. So translation and reflection from geometry should sound familiar. Stretches and shrinks are going to be a little bit different. They're going to kind of work like dilations did in geometry. So first off, we've got a translation. A translation is something that shifts the graph horizontally and or vertically and does not change its size, shape, or orientation. So for instance, if I have a graph of a function, let's say my function looks like this, it's an absolute value function. Let's say it's at the origin. I didn't draw that very well, but it could be shifted. Let's say it gets shifted vertically. My new function might look something like this. The same function, still an absolute value, but the whole thing got shifted up some number of units. Or it could get shifted up and, or let's say down and over. Maybe it got shifted like this. It's the same function given my drawing. It just had been shifted now to the left and down. And a nice way we can figure out what's happening is we can look at that point at the end. The point got moved up here by several units, or it got moved over to the left and down several units on the blue graph. So that's a translation. A reflection is a transformation that flips a graph over a line called the line of reflection. A reflected point is the same distance from the line of reflection as the original point, but on the opposite side of the line. So I'm going to do a reflection. I'll do that a little bit farther away. I took up more space than I should have. So this is a translation. This is going to be a reflection. So let's say I've got a function, looks like that. And let's say I want to reflect it over a line. That was terrible. Let's see if I can. I'll take it a little slower. Still terrible. So let's say that's my reflection line. And I'll do green for my new graph. Every point, I'm going to zoom in on this. Every point on my function gets reflected to a new point on the opposite side of the line of reflection. And then if I take all those points and reflect them, what I end up getting is a different picture of my original graph. And that results in a reflected function over that line of reflection. The line of reflection can be a horizontal line, or it could be, the line of reflection can be a vertical line, or it can be a horizontal line. If it's a vertical line, the reflection is a horizontal reflection. And if it's a horizontal line, the reflection becomes a vertical reflection. I could take these same points and reflect them vertically over my horizontal line and create a reflection of the function that looks like an upside down version of the original. So that's a reflection. And then finally, we've got a stretch or shrink. This is kind of the hardest one to get your head around. We'll be working on this a bit, but a stretch or a shrink is a transformation that multiplies all the y coordinates by the same positive factor, a factor other than 1. If the factor is greater than 1, then the transformation is what's called a vertical stretch. It gets stretched out vertically. If the factor is between 0 and 1, it's what we call a vertical shrink, and it's like the whole graph gets compressed down. And I'll give a quick example of that. We'll do some problems in a little bit that goes into it a little bit more, but let's start with this. Okay. So let's do, this is stretch or a shrink. So let's say this is my original function again, absolute value function, just doing its thing. If I stretch it out, what that's saying is all my y values are being multiplied by some number larger than 1. So if my y value here is, I don't know, 1, I double it. If my value here is 2, I double that, and so on and so forth. And what that does is it results in everything getting steeper vertically and then narrower horizontally. It's like every point on the red graph was grabbed and stretched away from 0, making it taller and making it go up faster. A shrink is just the opposite of that. For a shrink, if I've got my absolute value function The same thing holds if I'm multiplying by some number between 0 and 1. Let's say I'm multiplying by a half, which is going to cut it in half. Any value I have is going to get shorter. I'm going to zoom in on this. Try it again here. What the? So every value is going to get basically cut in half. This value here gets cut in half. This value up here gets cut in half. 0 get cut in half, still stays 0. And what that results in is a graph that doesn't grow quite as quickly vertically and looks like it's been flattened or compressed down. So it's a wider looking graph than a narrower looking graph. In class, remind me to talk about the rubber band example, and I will show how that looks when we look at a rubber band as a real life example of a stretch and shrink. All right. So our goal number 2 is graphing and describing transformations. There's a lot to this little section right here. We've got 7 different ones. We're going to try to get through them pretty quickly. So we're going to be using the parent function, f of x equals the absolute value of x. So the absolute value function. We know it looks like a v, so we can see that difference very easy. We're going to graph the following functions, and then we're going to describe, let's fix that. We're going to describe the domain and range, and then also describe the transformation from the parent function. I'm going to zoom in so we can save some space. So our first function is g of x equals x plus 1. So all my functions, I'm going to start with the absolute value functions. This is what we're referring to every time. So if I want to graph the function g of x equals the absolute value of x plus 1, and I want to figure out what's happening here, the best way to do that, to graph it correctly at least, would be to do an xy table. And with xy tables, my rule of thumb is to use the values -3 through +3. The reason we do that is because these numbers are all around the origin, and it makes it just a lot easier to see what is happening. So I'm going to plug these values in one at a time. Remember, my function is just x plus 1 in absolute value. So if I plug this in for y, I'll extend this out a little bit. I'm going to write this first one out. I'm plugging in -3 plus 1 into my absolute value, which is going to be the absolute value of -2, which is actually equal to 2. I'm going to do this for each of these. I'm going to zoom in a little bit more. I'm going to do this for each of these. I'm going to take -2 plus 1, and then that's going to be equal to the absolute value of -1, which is equal to +1. If I do -1, -1 plus 1 inside the absolute value, do the math, we get absolute value of 0, which is 0. And we'll keep on going through here. 1 plus 1, absolute value of 1, which is 1. 1 plus 1, absolute value of 2, 2. 2 plus 1, absolute value of 3, 3. And finally, 3 plus 1, absolute value of 4 equals 4. So I've got my inputs and my outputs now. If I input a -3, I get out a +2. If I input a -2, I get out a +1, and so on and so forth. So if I do that, I end up getting the following picture. So this is what my normal absolute value looks like. I'm going to do another one over here. I'll do this one in blue. So I've got these values, -3, +2. I'm going to go over 1, 2, 3. That's terrible. Let's zoom in and try that again. This is where it's a little bit difficult to get a good handle on this stuff when you're using online versus a real life whiteboard, but we're going to do our best. I plug in a -3, go over to the left 3, go up 2. Let's go 1, 2. It'll be something like that. -2 up +1, something like that. -1, 0 will be right about there. And then finally, I'm going back up at 0, +1, 1, +2, 3, or 2, +3, and 3, +4. I've got my values, and if I now connect them, it looks like my absolute value function looks effectively the same as the other one, except it's a messy drawing, but everything has been shifted to the left by 1 unit. So if I want to describe this transformation from the parent function, I can just say, okay, well, from the parent function, which looks, I'm going to overlay it, it looks like this. From the red function to become the blue function, I have translated to the left 1 unit. And that's it. Let's see here. Oh, we need the domain and the range. Well, my domain is going to be the same. I can put any x value into this function. So my domain, it's going to be all x values. And my range are going to be my y values, my outputs. Well, it looks like my y values, the lowest y value I can get, it looks like, is going to be 0. Right? I can't go below 0, but I can definitely get to 0. And then as I move to the left or to the right, if I move to the left or to the right for my range, I go up as I go to the left and right. My y values get higher. So my range is going to be all the y values greater than or equal to 0. And there we go. I know that was a lot of work for this first function, g of x. But making the chart helps us determine what is going on in the graph. All right. Let's try the next one. I'm just going to erase this stuff. This works pretty well to try to save some room. Hopefully I won't leave too much debris as I go along here. All right, that worked pretty nicely. All right, so let's do the next one. We already know what our parent function looks like. In fact, I'm going to draw it just very small up here. When I do graph the function at the end, I will overlay it, but I don't want to take up the room. So I'm dealing with h of x. That's our next one. We're doing this one now. Again, I'm going to create a table. My inputs versus my outputs. And I'll do the math on the output side. I'm going to pick -3 through +3. We'll zoom in here. And our equation in this case is x minus 3. So I'm going to plug in this into the absolute value. My x value is -3, plug that in. I'm going to subtract 3 from it. Well, that's going to give me the absolute value of -6, which is going to give me a value of +6. I'll very quickly go through these. Just keep stepping through it here. So now I've got all my values. If I plug in a -3, I get a +6. If I go up to +3, plug that in, I end up getting a 0 out of it. So let's quickly graph this, see what the heck is going on. So my original function looks like this. Change colors to differentiate. If I were to plug in, let's say this is 1, 2, 3, 1, 2, 3. If I'm going to plug in a -3, in this case, it's going to give me a +6. So I'm going to be way up here. If I plug in a -2, I'm going to get a +5. Plug in a -1, I get +4. 0, I get +3. 1, I get a +2. 2, I get a +1. And 0 or 3, I get a 0. And what that ends up doing, my graph is not the best, but it gives me something that looks like this. And I forgot, I should not make assumptions. I drew this right side line going back up. Let me show you what happens at +4, +5, and +6 really quickly. Here's 4, 5, and 6. At 4, I would get 4 minus 3 equals the absolute value of 1, which is 1. At 5, I would get 5 minus 3, which is equal to the absolute value of 2, which gives me 2. And at 6, I would get 6 minus 3, which is the absolute value of 3, or 3. So if I were to continue my chart over here with 4, 5, and 6, I would have gotten 4, 1, 5, 2, 6, 3. So it starts going back uphill after we reach 3 on the x-axis. If I were to compare that, again, to the graph of the original function, it looks like it has translated three units to the right, or in a positive direction on the x-axis. So that's interesting. On these first two, when I have addition or subtraction happening inside the absolute value, it's translate, and it's horizontal. Let's go to these next two, j of x and k of x. I'm going to do them both at the same time. I don't want to spend a ton of time on this. I know this is kind of going slow. I feel like I'm already taking too much time for this explanation. I don't want to bore you guys to death. So let's try to jam through these next two. In a more quick manner. So I'm going to set up two outputs. I'm going to use the outputs. I'm going to talk about the outputs as the function values. Remember, you may remember this from geometry. G of x is the function value. That's interchangeable with our y value, our output. So I'm going to have x, I'm going to have j of x, and I'm going to have k of x. We're going to kind of go faster on the math part as far as calculating this stuff. I'll still talk through it, but I want you guys to see what happens here. So if I have a -3 in my absolute value for j of x, absolute value of -3 is going to be +3. I'm going to add 2 to that. That's going to end up giving me a 5. If I take 2, absolute value of -2 is +2. I add 2 to that, it gives me a 4. Absolute value of -1 is +1, add 2, I get 3, and then 2. And then it starts going back the other direction. Absolute value of 1 is +1, add 2, I get 3, 4, and 5. So 5, 4, 3, 2, 3, 4, 5. And then on the k of x, if I plug in the absolute value of -3, I get +3, minus 4 gives me -1. -2 for x gives me an absolute value of 2, minus 4 gives me -2. We get -3, -4, and then I start going uphill again here, -3, -2, and -1. So with this chart, I've got x values for inputs, and I actually have 2 sets of y values for outputs, my j of x values and my k of x values. So again, I'm going to zoom in on this and try to do this as best I can. Let's take this 1, 2, 3, 4, 1, 2, 3, 4. And I'll count up, 2, 3, 4, count down, 1, 2, 3, 4. So remember, my parent function looks something like this. When x is 1, y is 1. When x is 2, y is 2. When x is -2, y is still +2. Let's compare that. I'm going to use a different color here to keep track of things. Let's use purple or pink for j of x. When x is -3, j of x is +5. Was it +5? Let's check again. Yes, +5. So -3 up +5. When it's -2, it becomes +4. When it's -1, it's +3. And then when it's 0, it is +2. Okay. So I've got 5, 4, 3, 2, and then I go back up to 3, 4, 5 in the other direction. And what that does is it creates our V-shaped graph. But in this case, it looks like it's been moved up a couple notches. In fact, we can say that j of x is translated two units up. Now let's do k of x. I'm going to use orange for that. Orange for k of x. When it's -3, my k of x is -1. When it's -2, I have a -2. -1, I've got a -3. And at 0, I've got a -4. It goes back up the other direction as I move back in a positive direction. And what that results in is, again, my same shape, but in this case, it's been moved down some units. And I could say that k of x is translated, 4 units down. If I'm thinking about domain and range, for all of my functions here, they all have the same domain. And that domain is all x values. my range will be different. For my orange function, my range, my lowest y value is going to be at -4, and it has no limit as I move up. So y will be greater than or equal to -4. For my pink function, same idea, except my lowest y value on the range is going to be y is greater than or equal to +2. So you may be seeing a pattern here based off the equations. My domain and my range, my domain doesn't really change, but my range is affected by the equations. On the pink graph, it was up by 2. On the orange graph, it was down by 4. The domain started at, or the range started at +2 for the pink, -4 for the orange. And these two functions both did vertical translations. So it moved it up or down on the graph. All right, those are translation graphs. Let's look at these last three. And these ones I'm multiplying, so things are going to get crazy again. I'm going to erase this stuff that's in the way. And we're going to deal with m of x. So our function name is m this time. And it's equal to the negative of the absolute value of x. So I take the absolute value first. I'm going to continue with the function notation. I take the absolute value first, then I'm going to stick a negative on it. So -3, -2, -1, 0, 1, 2, and 3. Absolute value of -3 is +3. I put a negative back on it, gives me -3. Same with -2, same with -1. There is no such thing as -0. And then if I plug a 1 in, absolute value of 1 is 1, negative of that is -1, -2, and -3. If I'm to graph this, here's my parent function. Let's use green this time. If I plug in -3, 1, 2, 3, go down 3, I get a value down there. -2, go down 2, get a value around there. 1 and 0. And if I go the other direction, I still get negatives. And what this results in is a reflection. This was a reflection that was reflected vertically. Every value that was up here is now down at the bottom. Every value that's up here on the left is now on the bottom left. It's like there was a mirror, in this case, right along the x-axis that everything got reflected over. So the description is a reflection, a vertical reflection in this case. We'll talk about horizontal reflections later on. Those are also possible, but right now we're just going to talk about vertical reflections. So it looks like when I multiplied everything by a negative, I got a vertical, reflection. All right, 2 more to go. I'm multiplying on these ones as well. We'll do the work down here. I've got P of x is 2 times x, and Q of x is 1/3 times x. I'm going to create a table again, and I'm going to combine P of x and Q of x into this table. I'm going to have 3 columns. Let's zoom in here. So I got my numbers, -3, -2, -1, 0, 1, 2, and 3. Well, if I take the absolute value of -3, that's going to give me a +3. And if I then multiply that value by 2, what that's going to do is give me the value 6. -2, absolute value is 2, times 2, 4. 2, 0, it's a terrible looking 0. If I take the absolute value of 1, I get 1, multiply it by 2, I get 2, 4, and 6. I multiplied all those values by 2. If I go back to my other function, everything's being multiplied by 1/3. So if I take the absolute value of 3, -3, I get +3. Multiply it by 1/3, I'm going to get 1. -2 becomes +2 with the absolute value. If I multiply it by 1/3, I get 2/3. And so on and so forth. 1 times 1/3 is 1/3. 0 times 1/3 is 0. 1 times 1/3 is 1/3. 2/3. And 3/3, which is just 1. So now I've got some coordinates. I've got my x inputs over here. And then I've got outputs for both functions. This is for the first function, all my outputs. This is for the second function, all my outputs. If I wanted to chart this out or graph this out, draw my parent function. And then I'm going to graph my other functions. I'll do yellow for the first one. It looks like every value's just been doubled. So if I go over -3, for instance, my output is going to be up here at 6 somewhere. Over -2, multiply it by 2, I'm going to get +4. -1, absolute value is 1, multiply it by 2, I get a +2. 0 just gives me 0. And then in the other direction, I'm going to get something that looks like this as well. And if I graph it out, I get my absolute value function, but it's steeper. It goes vertical faster, and it's narrower. It's like the sides have been brought in. So that's going to be my p of x function. And then let's do orange, my other one. Same idea. If I go over 3, I'm just going up 1 this time, so it's going to be a little bit lower. If I can do this correctly, let's see. It's going to be a little bit lower. And what this is going to result in, if I graph all these values, is a function that is far less steep. It's a much more gentle incline. And it's like the sides have been widened, or the whole thing's been flattened. This will be my q of x. And if I wanted to talk about these, I could say that p of x is a vertical stretch by a factor of 2. It's like everything has been multiplied by 2. And then finally, q of x, the last one, that is like a vertical shrink by a factor of 1/3. That's an A vertical shrink by a factor of 1/3. Everything's been multiplied by 1/3, so everything got way smaller. All right. That was the long part of this chapter. Oh, and I forgot domain and range on both of these. We talk about the domain on the reflection one really quick. Domain is still all real values of x. So all x. The range is all y values that are less than or equal to 0, because the function is now pointing downwards on the reflection. All my y values are in the bottom half of my graph, which means they're all negative values. Domain and range for p of x and q of x, these are pretty straightforward. My domain and range on both of them My domain is going to be all x values. All x values. My range, my outputs, there's not really much difference on them. It's just how quickly they're increasing. My range for the top one is still going to be y is greater than 0 or equal to 0. And for the q of x, the flatter one, it's also going to be y is greater than or equal to 0. So the domain and ranges on these two match because this point here hasn't been moved up or down by a translation. And the direction that the graph is pointing hasn't been flipped by a reflection. So the range stays the same. All right. Last goal. One problem here. We're combining transformations. So we can use more than one transformation at a time to graph the function. And our goal here is to graph this function, g of x equals negative absolute value of x plus 2 minus 3. We're going to describe the domain and range, and we're going to describe the transformations. So if we want to graph this out, my goal here is to figure out what's happening. So let's do that first. I'm going to have my x values and my g of x values. I'm going to use the same ones I've been using. -3 through +3. If I plug these in, I'm going to do the first couple longhand. Negative my x value, which is -3, plus 2 minus 3. Well, that's equal to -3 minus 2 becomes -5. And then I've got a minus 3. I can then do the absolute value. The absolute value of -5 becomes +5. So it's +5, which is -5, because I still have this negative sign on the outside as well. Minus 3. -5 minus 3 is -8. Quite a bit to that. Oops, I goofed up. I didn't do my addition correctly. I wasn't paying attention. So let's clean this. Apologies, guys. Everybody makes mistakes, even math teachers who have degrees in math. Let's plug this in again. Negative sign. Absolute value, -3 plus 2 is actually going to be -1. Minus 3. I can now take the absolute value of -1. That's going to give me +1. I still have this negative sign on the outside. -1 minus 3 is going to give me -4. That makes more sense. I'll write this one out as well. Plug in my -2. Work the inside of the absolute value first. I get 0. Keep working things. -0 is just 0. And then 0 minus 3 is -3. Do one more. Negative of 1, of absolute value of 1 minus 3. Absolute value of 1 is 1. I get -1 minus 3, which is going to take me back to -4 again. And then I'm just going to work these ones out quickly. And then these last three, I'm going to get -6, -7, and -8 if I work them out. So I've got a whole bunch of values. I'm going to rewrite this table. I want to condense things. So I'm going to use these values for my outputs to go with my inputs. So I'm going to write it out here in the void. My x value, and what's our function name? Is it g of x? G of x. So -3, -2, -1, 0, 1, 2, 3. If I put these in, I get these values out. So if I wanted to graph this out, I would get a function that looks a little bit different. If I go over to the left 3 and that down 4, I'll get a value around there. Over 2, down 3. Over 1, down 4. It's hard to draw these points sometimes. 0, down 5. 1, down 6. 2, down 7. And 3, down 8. And what that does, if I drew it all together, it would create a function that looks like this. It's my absolute value function. The point of that function is over here at, zoom in a little bit. The point of this function is at -2, -3. This is not to scale, it doesn't look perfect, but I'm at -2, -3. This point next to it would be -1, -4. Over here would be -3, -4, and so on, if I wanted to graph all my points. So I've got this upside down absolute value. It looks like the point has been moved. So remember, let's compare this to the standard absolute value graph. So it looks like the point has been moved over a little bit. It's been moved down. And then the whole thing has been reflected. So it's like the whole graph got shifted and moved. Can I pick this up? Let's see. Might be able to pick this up. Oh, that doesn't work very well. Never mind. It's like the whole graph has been moved to the left a certain amount of units. In this case, it looks like it's been moved to the left by 2 units, or moved -2 on the x-axis. It's been moved down 3 units, and it's been reflected over the x-axis. So if I wanted to write about this, I'd say that the graph of g of x is translated, I'm just going to put TR, period, 2 units left, 3 units down, and it's been reflected vertically. It's been flipped vertically. What's interesting, if we look at this graph here, or the equation, my equation was g of x equals negative x plus 2, did I get that right? Minus 3. Well, look at this. We've got this plus 2 right here. That's going to be my 2 units left. This -3 on the outside is going to be my 3 units down. And then this multiplication by a negative on the outside of my absolute value, that's going to be my reflection. So the goal here, as we get better with this, is understanding what causes the reflection, what causes the movement up and down, what causes the movement left and right, what causes stretches and shrinks, without having to put a table together and draw it out, but just by looking at the description of the equation, I can go, okay, I've got a negative sign, that's a reflection. I'm adding inside the absolute value, that's going to move it left and right, and since it's adding, I'm actually going to go to the left. And then I've got -3 on the outside, that's going to be a shift, it's going to shift it down. And you can put that together really fast once you get the hang of looking at these different types of transformations. All right, that is it for this lecture. This was a very long lecture. I apologize. I got to work on this pacing. Homework will be assigned through Teams. You'll get the notification for that at the same time as you get the notification, excuse me, at the notification for this video becoming active. If you have questions, you can email me, message me on Remind, or if they're not super pressing, you can always wait and ask them in class. All right, guys, thank you very much and have a great day.